Okay, so now I'm going to explain to you the formula for the dot product between two vectors. Remember last time I gave you the geometric interpretation for the dot product, which is that if you have two vectors u and v making a certain angle theta between them, then u dot v is the same as the norm of u times the norm of v times the cosine of the angle between them. Okay? And as a special case of this formula, you should remember that we know that if you take u and v to be the same, you obtain that u dot u cosine of 0 is 1, so you get u squared, the norm of u squared, right? Which we will use in a second. And the other important formula that we will use soon is that if you take two vectors which are perpendicular to each other, then their dot product is 0. If perpendicular. So why are these two facts useful? Well, remember that when you want to do computations with vectors, it's useful to use a coordinate system. So let's use a coordinate system, and if you use a coordinate system, then you have, first of all, the two unit vectors that we have discussed in the past. So let's call that I and j. Again, they're unit vectors. So in particular, that means that what is I dot I? Well, this is the dot product of a vector with itself. If you use this formula, it's the norm of I squared, or the magnitude squared. But the norm, this is unit vector, so by definition its size is 1. So 1 squared is still 1. So the dot product of I with itself is 1. By the same logic, the dot product of j with itself, again use this formula, is the norm, the magnitude of j squared, and that's still 1. And finally, the dot product of I and j, that's important to know. Well, the angle between them is pi over 2. So the dot product is 0 because they're perpendicular, right? So that's why all those properties were useful. Now, let me derive the formula for the dot product. So suppose you have a vector u, which is here. Again, let me just move them around. That's called, remember that you can put u and v wherever you want. So let's, you can move them to the origin. Let's say that u is there and v is here. So maybe u represents a point x1, y1. V represents a point x2, y2. So what is u dot v? Not using this formula, but rather using these properties. Well, remember that a property of the unit vectors is that you can decompose any vector in terms of these. So you can write u as x1 I plus y1 j, and v you can write as x2 I plus y2 j. And while we'll take for granted the fact that when you do a dot product, you can sort of distribute in the naive way that as you would have if you just thought of these as ordinary numbers, meaning that you can do this one, which would give you x1, x2, I dot I, then x1, y2, I dot j, plus y1, x2, j dot I, plus y1, y2, j dot j. Okay, and so again we come back to these properties where I dot j and j dot I are 0 because they're perpendicular, right? And then I dot I equals 1 because we just found that before, and j dot j equals 1 as well. And so this goes away, and you end up with x1, x2 plus y1, y2. Okay, so the big summary of all of this, let me write it separately. Is that if you do a dot product between x1, y1 and x2, y2, then that's the same as multiplying the corresponding entries. So the first entry with the first entry of each vector plus the second entry with the second entry of the second entry of the first vector with the second entry of the second vector. So the dot product consists of, from this algebraic perspective, of like two individual multiplications which are added with each other. Okay, so now in the next video I'll just do some examples and tell you some useful ways that you can play around with this formula.